Hello, my dear students. Welcome to IKSR chemistry classes. In this video, we will discuss Jahn Teller effect or Jahn Teller theorem. It is an important topic in the chapter of complex compounds, that is coordination compounds, and questions related to it are asked frequently in various competitive examinations as well as general examinations. First of all, let us see distortion in octahedral complexes. This is an octahedral complex in which all the six metal ligand bonds are of equal length. The octahedral complex in which all the six metal ligand bonds are of equal length is called a regular octahedral complex. It is an example of regular octahedral complex in which all the six metal ligand bonds are of equal length. It means this ML1 bond length is equal to ML2 bond length is equal to ML3 bond length, and it is also equal to ML4, ML5 and ML6 bond lengths. All the six metal ligand bonds are of equal length. And such complexes are called regular octahedral complexes. On the other hand, the octahedral complex in which all the six metal ligand bonds are not of equal length is called a distorted octahedral complex. The tetragonally distorted octahedral complex are more common, in which distortion takes place along fourfold axis of symmetry. Please note that the octahedral complex in which all the six metal ligand bonds are not of equal length is called a distorted octahedral complex, and the distortion in octahedral complex may take place in various ways. It is an octahedron. It is fourfold axis of symmetry C4, and about the distortion in octahedral complex takes place along C4 axis of symmetry. It is called tetragonal distortion, and such complexes are called tetragonally distorted octahedral complex, and it is the most common one. This is C3 axis of symmetry, threefold axis of symmetry, which passes through the centers of two opposite faces. It is C3 axis of symmetry, and if the distortion in octahedral complex takes place along C3 axis of symmetry, it is called trigonally distorted octahedral complexes. And this axis is C2, not C3. It is C2, which passes through the centers of two opposite edges. This axis passes through the centers of two opposite edges. It is twofold axis of symmetry, and if the distortion in octahedral complex takes place along twofold axis of symmetry, it is called diagonal distortion. Diagonal distortion, trigonal distortion and tetragonal distortion. And out of these three types of distortions in octahedral complex, tetragonal distortion is the most important one. The tetragonally distorted octahedral complexes are two types. Are of two types. Let us see. Jade out or elongation along Z axis. It is an octahedral complex in which two bonds along Z axis ML1 and ML6 are longer metal ligand bond, while the four bonds which are situated on the xy plane are shorter. Such distorted octahedral complexes are called Jade Out distorted octahedral complexes. In such complexes, two metal ligand bonds along the z-axis are longer than four metal ligand bonds on the xy plane. It means ML1 is equal to ML6, which is longer than ML2, ML3, ML4 and ML5. Two bonds on the z-axis, that is ML1 and ML6, are longer than the four metal ligand bonds situated on the xy plane. And this type of distortion, this type of tetragonal distortion in octahedral complexes is called Jade Out or elongation along z-axis. The another type of tetragonal distortion is Jade In or compression along the z-axis. It is the example in which two bonds along the z-axis ML1 and ML2 are shorter. That is, the bonds on the z-axis have been compressed, while the four metal ligand bonds on the xy plane are longer. In such tetragonally distorted complexes, two metal ligand bonds along the z-axis are shorter, are compressed than four metal ligand bonds situated on the xy plane. It means ML1 is equal to ML6, which is shorter than, which is smaller than four metal ligand bonds situated on the xy plane, that is ML2, ML3, ML4 and ML5. Thus, the tetragonal distortion in octahedral complexes is of two types, Jade Out and Jade In. Let us see a few examples. It is CuF2, which has octahedral geometry of 6 F- ions around the central metal ion, that is Cu2 plus ion. The four metal ligand bonds on the xy plane have bond length 193 picometer, while the two bonds situated on the z-axis have bond length 227 picometer. It is obvious that the bonds on the z-axis are longer than the four bonds on the xy plane, and hence it is an example of Jade Out tetragonally distorted octahedral complex. And in another case, Fe2 plus ion also has octahedral arrangement of 6 F- ion ligands. In this case, the two bonds on the z-axis have bond length 199 picometer, and it is shorter than the four metal ligand bonds on the xy plane having length 212 picometer. Here, two bonds along the z-axis are compressed are shorter in comparison to four bonds on the xy plane, and it is an example of Jade in tetragonally distorted octahedral complex. In 1937, Jahn Teller proposed a theorem in order to explain the distortion in octahedral complexes as follows. Any non-linear molecular system having orbitally degenerate electronic state will be unstable and it will undergo distortion in geometry to form a system of lower symmetry and lower energy, and thus the degeneracy of the electronic state is removed partially or completely. Let us understand it again. Any molecular system which is non-linear and has degenerate orbitals, that is orbitals with same energy, will be unstable. Such system will be unstable and will undergo distortion in geometry in such a way that the symmetry and energy of the system becomes lower, and as a result the degeneracy of electronic state may be removed partially or completely. Any molecular system which is non-linear in shape and has degenerate electronic state is unstable. It undergoes distortion in geometry in such a way that the new system formed has lower symmetry as well as lower energy, and as a result of this distortion the electronic state of the system, the degeneracy of electronic state of the system is removed completely or partially. It is known as Jahn Teller Theorem. And distortion in octahedral complex, distortion in the octahedral complex is called Jahn Teller distortion. This theory is known as Jahn Teller theorem, and this type of distortion is called Jahn Teller distortion. Let us see now cause of distortion in octahedral complexes. The distortion in octahedral complexes is due to the unsymmetrical filling up of T2G and EG set of orbitals. We already know that the 5d atomic orbitals of the central metal ion are splits up into T2G and EG sets of orbitals in an octahedral crystal field. The T2G set of orbitals is triply degenerate while EG set of orbital is doubly degenerate, and the distortion in geometry of octahedral complexes takes place due to unsymmetrical filling up of T2G and EG set of orbitals. The lobes of T2G orbitals lie in between the axes, that is away from the metal ligand direction, and hence the unsymmetrical filling up of T2G set of orbitals causes slight distortion in geometry. We already know that the lobes of T2G orbitals lie in between the axes, that is away from the metal ligand direction, and therefore the unsymmetrical filling up of T2G set of orbitals causes only slight distortion in the geometry. On the other hand, the lobes of EG orbitals lie on the axis, that is along the metal ligand direction, and hence the unsymmetrical filling up of EG set of orbitals causes a strong distortion in geometry, and it will be discussed mainly here. The vacant, half-filled and fulfilled set of orbitals is symmetrically filled. Please note that the vacant or half-filled or fulfilled set of orbitals is symmetrically filled, while any other electronic configuration is unsymmetrically filled. We already know that the T2G set of orbitals contains 3 orbitals, while EG set contains 2 orbitals. And now let us see the symmetry of various electronic configurations for T2G and EG set of orbitals. These are various electronic configurations in T2G set of orbitals. There are 3 orbitals in T2G set. It is half-filled. T2G3 is half-filled, while T2G6 is full-filled. Maximum 2 electrons with opposite spins can be accommodated in an orbital. Accordingly, when the configuration is T2G3, it is half-filled and symmetrical, and if the configuration is T2G6, it is full-filled and again symmetrical, while other electronic configurations T2G1, T2G2, T2G4 and T2G5 are unsymmetrical. In EG set of orbitals, there are 2 orbitals in which maximum 4 electrons can be accommodated, and therefore EG2 is half-filled and EG4 is full-filled, and these are symmetrical electronic configurations. EG0 is vacant, it is also symmetrical, while EG1 and EG3 are unsymmetrical electronic configurations. We have already seen that the Jahn Teller distortion arises due to unsymmetrical filling up of T2G and EG set of orbitals. The unsymmetrical filling up of T2G set of orbitals causes only slight distortion, while the unsymmetrical filling up of EG set of orbitals causes a strong distortion in geometry of octahedral complex. A strong distortion in octahedral complexes. The octahedral complexes of metal ions with following electronic configurations exhibit a strong distortion. D4, weak ligand field, has electronic configuration T2G3 and EG1. Here EG1 is unsymmetrically filled. D7, a strong ligand field. In a strong ligand field, D7 has electronic configuration T2G6 and EG1. First of all, T2G set of orbitals will be filled up, and then filling up of EG set of orbital takes place. EG1 is unsymmetrical, and similarly in the D9 transition metal ion has electronic configuration T2G6 and EG3. In these 3 electronic configurations of metal ions, the EG set of orbitals is unsymmetrically filled. D4 weak ligand field, D7 a strong ligand field, and D9 in both weak and strong ligand field, EG set of orbitals is unsymmetrically filled, and a strong distortion in octahedral complexes takes place. Jahn Teller Stabilization energy which may be abbreviated as JTSE. The decrease in energy due to distortion, that is a splitting of electronic energy levels, increases the stability of the system, and hence it is called Jahn Teller Stabilization energy. We have already seen that. We have already discussed that the a splitting or of electronic states or distortion in geometry leads to decrease in the energy of the system and increases the stability of the system, and hence this decrease in energy is known as Jahn Teller Stabilization energy. The distortion will occur in octahedral complexes in such a way that there is maximum Jahn Teller stabilization energy. The distortion in octahedral complexes will take place in such a direction, in such a way that there is maximum Jahn Teller stabilization energy. A splitting of electronic energy levels, that is orbitals, in distorted octahedral complexes. In a free transition metal ion, all the 5d atomic orbitals have the same energy, that is are degenerate. In free transition metal ion, 5d atomic orbitals have the same energy and they are degenerate. But when the transition metal ion forms an octahedral complex, d atomic orbitals are split up into two sets. The first set of orbitals is T2G set. It contains dxy, dyz and dxz atomic orbitals, while the other set, Eg set, contains dz square and dx square minus y square atomic orbitals. In octahedral crystal field, these three atomic orbitals have lower energy, while these two d atomic orbitals have higher energy. Further, a splitting of orbitals takes place in the case of distortion from regular octahedral geometry. If distortion from regular octahedral geometry takes place, these two sets further undergo a splitting depending upon the conditions Jade in or Jade out. A splitting of d atomic orbitals in Jade out octahedral complexes. In Jade out octahedral complexes, two ligands on the Z axis move away from the metal ion. That is, two metal ligand bonds along the Z axis are elongated. These are 5d atomic orbitals of the metal ion in a spherically symmetrical crystal field. When the metal ion forms a regular octahedral complex, these 5d atomic orbitals are split up into two sets. The lower energy set of d atomic orbitals containing dxy, dyz and dxz atomic orbitals is called T2G, while the higher energy set of d atomic orbitals containing dz square and dx square minus y square orbitals is called Eg set, and the energy difference between these two sets of orbitals is called delta O, that is crystal field splitting energy in octahedral crystal field. These are d atomic orbitals of the metal ion in distorted octahedral crystal field with Jade out. If the ligands on the Z axis move away from the central metal ion, the orbitals containing Z component have lower energy. Because the ligands on the Z axis have moved away from the central metal ion. As a result, the electrons present in atomic orbitals containing Z component experience lower repulsion, and hence the energy of orbitals dxz and dyz containing Z component decrease, while the energy of d atomic orbital having no Z component increase. Similarly, in this case also, the energy of dz square atomic orbital decreases because its electron experiences lower repulsion from the ligands. On the other hand, the energy of dx square minus y square atomic orbital increases because its lobes are encountered by 4 ligands, and the electron present in this orbital experiences greater repulsion. This type of splitting takes place due to distortion in regular octahedral geometry with Jade Out. It is delta O. This energy difference is called delta 1 and this is called delta 2. It is obvious that delta O is much greater than delta 1 and delta 1 is greater than delta 2. Similarly, let us see a splitting of d atomic orbitals in Jade Out. It should be Jade in, not Jade Out. Jade in octahedral complex. It is Jade in. In this type of distortion in octahedral complexes, two ligands on the Z axis move closer to CMI. As a result, the electrons present in d atomic orbitals having Z component experience greater repulsion, and therefore the energy of dxz and dyz atomic orbitals increases. Similarly, the energy of dz square atomic orbital also increases because these d atomic orbitals have Z component, and the ligands on the Z axis move closer to CMI, and the ligand field strength along the Z axis is stronger, and this is why the d atomic orbitals having Z component suffer from increase in energy. On the other hand, the d atomic orbitals having only X or Y component suffer from decrease in energy. This type of splitting of d atomic orbitals takes place in octahedral complexes with Z in distortion. Here also delta O is much greater than delta 1 and delta 1 is greater than delta 2. There is a state of dilemma. In the case of Jahn Teller distortion caused by unsymmetrical filling up of EG set of orbitals, the Jahn Teller distortion energies for Z out and Z in complexes are the same, and which type of distortion will take place cannot be predicted. If the Jahn Teller distortion in octahedral complexes takes place due to unsymmetrical filling up of EG set of orbitals, the Jahn Teller stabilization energy for Z out and Z in configurations is the same, and which type of distortion will take place cannot be predicted. Let us see electronic configuration of metal ion Eg1. This is unsymmetrical filling up, and Eg3, this is also unsymmetrically filled. The Jahn Teller stabilization energy for Z out and Z in configurations is the same for Eg1, and for Eg3 also the Jahn Teller stabilization energy is same for Z out and Z in, and therefore the type of distortion may be either Z in or Jade Out, which will take place, we cannot predict with certainty. Let us see an example. Cu2 plus ion has electronic configuration 3d9. Electronic configuration of Cu2 plus in octahedral crystal field will be T2G6 Eg3. Eg3 set of orbitals is unsymmetrically filled. Jahn Teller distortion energy in Jahn Teller stabilization energy in Jade in configuration is minus 1 by 3 delta 2, and in the Jahn Teller stabilization energy for Jade Out configuration it is again minus 1 by 3 delta 2. The Jahn Teller stabilization energy for Jade in and Jade Out configurations is same. Thus, the type of Jahn Teller distortion cannot be predicted. In CuF2, there is Jade Out Jahn Teller distortion, while in the similar complex, Jade in Jahn Teller distortion is observed. Thus, the actual type of distortion, Jade in or Jade out, cannot be predicted theoretically. The same Cu2 plus ion exhibits Jade out distortion and Jade in distortion in different cases. But there is a state of confidence in the case of Jahn Teller distortion caused by unsymmetrical filling up of T2G set of orbitals. The Jahn Teller stabilization energies for Jade out and Jade in complexes are different, and which type of distortion will take place can be predicted with certainty, with confidence. These are unsymmetrical filling up of T2G set of orbitals, T2G1, T2G2, T2G4 and T2G5. And these are Jahn Teller stabilization energies. In T2G1, the Jahn Teller stabilization energy in Jade in is greater than that in Jade out, and therefore Jade in distortion will take place. For T2G2, the Jahn Teller stabilization energy for Jade out is greater than that in Jade in configuration, and therefore Jade out distortion will take place. In T2G4, the Jahn Teller stabilization energy in Jade in configuration is greater than that for Jade out configuration, and therefore Jade in distortion will take place. The Jahn Teller distortion takes place in such a direction that there is maximum Jahn Teller stabilization energy. In the case of T2G5, the Jahn Teller stabilization energy in Jade out configuration is greater than that in Jade in, and therefore Jade out distortion will take place. Thus, the type of Jahn Teller distortion, Jade in or Jade out, can be predicted with confidence if this distortion arises due to unsymmetrical filling up of T2G set of orbitals. Let us see an example. Fe2 plus ion 3d6 in weak ligand field of F minus ions in FeF2, its electronic configuration will be T2G4 Eg2. Here T2G4 is unsymmetrically filled, and its Jahn Teller stabilization energy in Jade in configuration is minus 2 by 3 delta 2, and in Jade out configuration it is minus 1 by 3 delta 2. This Jade in, it is obvious that the Jahn Teller stabilization energy is greater in Jade in than that in Jade out. Jahn Teller Stabilization energy for Jade in distortion is greater than that for Jade out distortion, and therefore we can predict with certainty that Jade in Jahn Teller distortion will take place in FE2. Two bonds along z-axis are shorter, 1.99 angstrom, while the four bonds on the xy plane are longer. This is Jahn Teller distortion of the type Z in, which can be predicted from the Jahn Teller stabilization energy. Thank you for watching the video with patience and concentration. Please like and share it. And if you have not subscribed my channel yet, please subscribe it so that you may get information regarding my new videos in time. Thank you again.